In this presentation, we are going to have phasor diagram, voltage triangle, impedance triangle, and power triangle of series RLC circuit. And this is our series RLC circuit. And let us say that voltage VT is having the corresponding phasor representation as V phasor. Current IT, which is the current in this circuit, is having the phasor representation as I phasor. And the voltage phasor across resistor is represented by VR phasor, and the voltage phasor across the inductor is represented by VL phasor, and the voltage phasor across the capacitor is represented by VC phasor. And we can see here different types of elements are connected in series combination, and therefore the net voltage will be the phasor sum. This means V phasor will be equal to VR phasor plus VL phasor plus VC phasor. And we can say that these three elements together will provide an obstruction to the current flow, and that obstruction we call as the impedance. And let us say that the impedance offered by these three together is Z. And when you multiply I phasor with Z, you will have V phasor. Therefore, we can say that V phasor is equal to I phasor multiplied to Z. And VR phasor, it will be equal to I phasor multiplied to R. I phasor multiplied to R. VL phasor, it is equal to I phasor multiplied to JXL. So in place of VL phasor, we can have JXL multiplied to I phasor. And VC phasor, it will be equal to I phasor multiplied to negative of JXC. So we can have negative of JXC multiplied to I phasor in place of VC phasor. Now when you take I phasor common and cancel it out with this I phasor, you will have Z, impedance Z, equal to resistance R plus J inside the bracket reactance XL minus reactance XC. So in this way we have all the relations to draw the phasor diagram, and the step number 1 to draw the phasor diagram is to choose the reference phasor. And I will choose I phasor as the reference phasor because current IT is same throughout the circuit. So this reference phasor is our current phasor. And when you focus on VR phasor, you will understand it is the voltage across the resistor, and it is equal to I phasor multiplied to R. This means it will have the magnitude lesser than I phasor, and it will be in the same phase as of I phasor because it is the voltage across the resistor. So this phasor is our VR phasor. Now moving on to VL phasor, it is the voltage across the inductor, and therefore it will lead the current by 90 degrees. And VC phasor, it is the voltage across the capacitor, and therefore it will lag the current by 90 degrees. And while plotting VL phasor and VC phasor, I have assumed that the magnitude of VL, that is the magnitude of the voltage across inductor, is greater than the magnitude of VC, that is the magnitude of voltage across capacitor. And therefore you can see that I have drawn this line larger as compared to this line. And we can have the resultant of VL phasor and VC phasor like this. It will have the magnitude VL minus VC. And we know that the sum of this vector and this vector will give us V phasor. Why? Because VL phasor plus VC phasor will be this vector, and VR phasor is this vector, and their sum is giving us V phasor. So the vector sum of this vector and this vector will give us this vector. And the angle between the net voltage phasor and the net current phasor we know is the power factor angle theta. So this is how the phasor diagram of series RLC circuit will look. Now we will move on to the voltage triangle. This angle will be theta. The hypotenuse will be voltage V. The perpendicular will be voltage VL minus VC, and the base will be voltage VR. We have taken this triangle and we are writing the magnitudes. Now from the triangle we can say that voltage V is equal to under root VR square plus VL minus VC square, VL minus VC square, and theta, the power factor angle, it will be equal to tan inverse VL minus VC, VL minus VC divided by VR, and the power factor cos theta, it is equal to VR divided by V. And whether the power factor will lead or lag, it will depend on the L and C values. So I'm not writing leading or lagging here because it is dependent on the values of inductance and capacitance. Now moving on to the impedance triangle, we have this angle as theta. The hypotenuse will be impedance Z. The perpendicular will be XL minus XC, and the base will be resistance R. So from here we can say that the impedance will be equal to under root R square plus XL minus XC square, XL minus XC square, and the angle theta, which is the power factor angle, is equal to tan inverse XL minus XC divided by resistance R, and the power factor cos theta, it will be equal to resistance divided by the impedance. And the last triangle is the power triangle. This side is the apparent power S, this side will be QL minus QC, which is equal to the net reactive power Q. The base will be the real power P, and S, the apparent power, it is equal to under root P square plus Q square, and power factor angle, it is equal to tan inverse Q divided by the real power P, and the power factor, it is equal to real power divided by the apparent power. So this is all for this lecture. See you in the next one.